Welcome back. In this unit we are going to hit the highlights of Chapter 16, The Sun. Please be sure that you read the entire chapter in the book, but in these mini lectures we're just going to focus on how the Sun is like other stars, so that next week when we talk about stars we have something to compare it with. So this is a recent picture of the Sun. It was taken on October 16th of 2012. And when you look at it, you notice that most of the Sun is just the nice plain canary yellow that we're used to. But then there are some parts, such as here, where we have sunspots. Some parts, such as here, where there are light white spots. These are called faculae. But otherwise, it's a fairly generic yellow. Some physical properties of the Sun. These are not things I expect you to memorize, but I want to point out some important relations and some important things to keep in mind as we go along. So the Sun has a radius of 700,000 kilometers. That's about 500,000 miles, and that radius is roughly 100 times the radius of the Earth. The mass of the Sun is 2 times 10 to the 30th kilograms. That's a number so big I'm not even sure what the exact name of it is. It's something like an octillion or nonillion or some number that is so big it doesn't make any sense to me anyway. But that mass makes it 333,000 times that of the Earth. And if we want to worry about density, density is how much mass you have and how much volume. As a guide to help you know what density is, water has a density of 1,000 kilograms per cubic meter. So if we had 1 cubic meter, that's an aquarium, a little over 3 feet on a side, filled that full of water, it would have a mass of 1,000 kilograms. And a slab of granite the same size would have a mass of 2,700 kilograms. So granite is denser than water. If we look at the average density of the Sun, it works out to 1,400 kilograms per cubic meter. So more dense than water, but less dense than granite. The Earth, which is made up of rock and iron, is more dense than granite, 5,500 kilograms per cubic meter. So on average, the Sun is less dense than the Earth. However, the Sun goes from extraordinarily dense in its core, 160,000 kilograms per cubic meter. So this is nearly 100 times denser than rock on Earth's surface. At the surface of the Sun, it is much thinner than Earth's atmosphere. The surface of the Sun has a density of 1/1,000,000th of a kilogram per cubic meter, and on the Earth it's about 1 kilogram per cubic meter. So the visible surface of the Sun is less dense than Earth's atmosphere by about a factor of 1,000,000. And if we go up into the Sun's atmosphere, by the time we get to the very outer reaches of what we call the solar wind, the Sun has a density of only 6 atoms per cubic centimeter. And here at the Earth, up where the space station and the space shuttle orbit, there's still a little residual atmosphere. I mean, so little that you would suffocate if you're out there. But there's still 10 million atoms per cubic centimeter at the level of the space station. And compare that with 6 atoms per cubic centimeter for the solar wind, and we find that it really is nearly a pure vacuum up at the upper end of the Sun. So the Sun goes from extremely dense at its core, far denser than any material on Earth, to extraordinarily tenuous at its upper surface and beyond. The Sun's luminosity, its total energy, is 4 times 10 to the 26 watts. Again, that's another huge number compared with things like 100 watt, 150 watt light bulbs. And that's the equivalent of 10 billion nuclear bombs per second, far more than we have on the Earth. So a huge amount of energy coming out of the Sun every second. And if we look at how much light from the Sun reaches the Earth, because the Earth only intersects a small portion of the total energy coming from the Sun, it works out to about 1,400 watts per square meter. So if you laid out a square meter on the ground, drew a square a little over 3 feet on a side, you'd be getting 1,400 watts in that square. And this adds up to many times the total human energy usage. So on average, humans use about 16 trillion watts of energy, and the Sun delivers over 10,000 times that much energy to the surface of the Earth. So in 70 minutes, in a little over 1 hour, if we collected all the sunlight that hit the Earth, we'd have enough sunlight to power all of our work, all human activities, for over a year. So, in other words, there's plenty of solar energy reaching our surface. If we could find any way to harvest even just a small fraction of it, we'd have more than enough energy for all our energy needs. So the middle of the sun, the temperature gets up to 15 million degrees Kelvin. That's 27 million degrees Fahrenheit, so extraordinarily hot at the center of the sun. Surface of the sun is relatively cold, at least compared to the center of the sun. The surface is 5,800 Kelvin, 10,000 degrees Fahrenheit. Still a little toasty for us, but again, far cooler than the center of the sun. Those dark sunspots on the surface of the sun have a temperature of 4,200 Kelvin, so cooler than the other surface. That's why they look darker, because if you remember, cooler objects do not radiate as much total light and radiate at a longer wavelength, so sunspots look orange or red. The corona of the sun, its very tenuous outer atmosphere, the temperature goes back up to about 1,000,000 degrees, which is extraordinarily hot, but again, it's so tenuous that there's not much heat energy there. And as seen from the Earth, the sun takes almost a month to make one complete rotation. The sun is made out of gas and plasma, so it does not have to rotate as a solid object. Different parts can rotate at different speeds. And so near the equator, the sun rotates every 27 days, while near the poles it takes over a month, 31 or 32 days, to do one complete rotation. If we look at what the sun is made out of, the sun is made primarily of hydrogen and helium. So about 74% of the sun by mass is hydrogen, about 25% is helium, and the remaining 1.5% is everything else, mostly carbon and oxygen, and a little bit of all the heavier elements. Now contrast that to the Earth, where the Earth has almost no hydrogen, almost no helium, and 99.96% of the Earth is everything else. So while the sun is 98.5% hydrogen and helium, the Earth is only 0.05% all of that. And this tells us that there were differences in the formation of the sun and the Earth, which we will get to here in a couple of chapters when we talk about starbirth. So let's now briefly go over the structure of the sun. Why does the sun stay stable? If we look at it day after day, it's the same size, and it's made out of gas. There's nothing that stops a gas from being compressed or from expanding. So why does the sun stay so stable from day to day? And if we look at the structure of the sun has layers like an onion or a parfait or an ogre. The inner part of the sun is the core of the sun. That's where the nuclear fusion happens. And that's surrounded by something called the radiation zone, which we'll talk about in the next mini lecture. So 70% of the sun, from the core to 70% of the way out, is this radiation zone. And then the outer third of the sun is almost completely something called the convection zone. The visible surface of the sun is called the photosphere. It's only a few hundred kilometers thick. And then we get into the sun's tenuous atmosphere, which has layers called the chromosphere and the corona. We're not going to worry too much in this class about those outer parts of the sun. Main things to remember are that the central part of the sun is the core and the radiation zone, and then most of the rest of the sun is this thing called the convection zone. And again, we'll talk about why they have these names in the next lecture. The sun is constantly fighting a battle between gravity and pressure. So imagine that you are these acrobats here. Which one would you want to be? I don't know about you. Maybe you are masochistic and would want to be the person on the bottom. I'd prefer to be the person on the top. If you want to stay stable in an acrobatic structure like this, each person lower on the pyramid has to exert more force against gravity to keep the weight of the people above them stable, so they don't all collapse down. The sun does the same sort of thing. The innermost gas of the sun, the innermost parts of the sun, have to exert some sort of force, and they exert pressure to keep the outer layers of the sun from collapsing inward due to gravity. Gravity is trying to pull the outer parts of the sun in, and the pressure of the gas in the sun is trying to push those parts outward. And so this is a constant battle that the sun has to fight, and clearly the sun has found some equilibrium state, some state where it's very stable. And so as you go inward, from the surface of the sun, At the very surface of the sun, you don't have very many layers outside of it, and so there's very little weight that has to be held up, and so the pressure of the gas is fairly low. As you go inward, the pull of gravity increases the weight of the layers above you, because there's more and more material above you, and so therefore in order to hold that still, the gas has to exert a higher pressure. And if you remember from chemistry classes in high school, if you have a gas and it's at a higher pressure, it will be at a higher temperature. This is the ideal gas law. Higher pressures mean higher temperatures, and so the sun gets hotter as we go inward, and this is something we already saw a few pages ago. So this explains why the sun is hotter in the center. It's not just because there's fusion going on. The sun is hotter in the center because the pressure squeezes the gas, which gets it up to the high temperature that permits fusion to occur. So in summary, here are the properties and structure of the sun. The sun is a ball of gas. It's made almost entirely of hydrogen and helium. 98.5% of the sun are those two elements. At the center of the sun, it's extraordinarily hot and dense. It's 15 million degrees, and it's 100 times denser than rock on Earth. The surface of the sun is much cooler, still warm for us, about 6,000 degrees, but the density is very thin, much thinner than our atmosphere. And then as you go out into the sun's atmosphere, its temperature increases more, but the atmosphere is extraordinarily thin. The sun doesn't rotate as a solid object. The equator of the sun rotates faster than the poles of the sun. And the sun is stable because of this equality of gravity pulling inward and pressure pushing outward. Remember those things, and as we go further on into this chapter, to explain why the sun is stable, why it remains stable for a long period of time. So that completes the first mini lecture.